my name is David Cater. In this video we're going to talk about a capacitive circuit in AC. So we're going to deal with a very basic circuit, and that's just a pure capacitor. In the circuit there will be no resistance. What we want to figure out is what's the ohmic value that the capacitor is going to impose on the system, and what's the total current, and what's the power in that system, and what kind of power is it. So we've got a 50 volt source at 60 hertz, and we have a 750 microfarad capacitor. All right, so it's a fairly large capacitor. Now, the very first thing we want to do is figure out what's the current limiting effect. And in this circuit, it will be XC, capacitive reactance. So the XC formula is 1 over 2 pi times F times C. And we just simply need to punch in the numbers to figure out what is the capacitive reactance in this circuit. So that is 2 times pi times 60 hertz times 750 times 10 to the negative 6 to make sure it's in microfarads. So what we end up getting here is a fairly small ohmic value, and that's 3.54 ohms. All right, so this is a very sizable capacitor at 60 hertz, and so therefore we don't actually expect it to be limiting current very much, and therefore we don't see it limiting current very much with only 3.54 ohms of resistance. It's not a very big ohmic value. All right, so what we want to do then is figure out what is going to be the current that's going to flow in this circuit. So we can figure that out with I is the E total over our impedance total. So that would be I total, E total over Z total. And in this circuit we only have XC, so that is our Z total, our impedance total. And so we'll just simply punch in the numbers here, and we have a 50 volt source, and we have a 3.54 ohm capacitive reactance. So we get an I total of 14.12 amps. All right, so that is it is what it is. It's a value of current, and I believe we're good. So from there, what we want to do then is figure out how much power is in this circuit. So we're not looking for watts, as we're going to assume this we have no resistance, and therefore we have no watts and no heat built up in our capacitor. This is going to be purely reactive power. So we're looking for Q, and we are looking for the Q of XC. And the Q of XC in this case, seeing as we have a value of XC and a current, we could use I squared through the capacitor times the value of XC, much like I squared R. So we can do that, and we will have 14.12 squared multiplied by 3.54, and we get a total volt amp reactive of 705.79 VARs. Okay, so that is the total amount of energy that's being stored in the electric field inside of this capacitor. So we have an electric field developed in here, and it is storing energy for us, and it will be returned to the circuit when given the chance. And so therefore we're not dissipating any watts, we're only really storing it, and every time the source flips from positive to negative, it gets returned, and this sort of storage and return cycle continues on and on and on. All right, so the last thing I want to do is then see what happens to this exact same circuit if we change the frequency to 30 hertz. So we're going to cut the frequency in half. Now, what we want to come to start to sort of get an intuitive idea on is the current going to go up? Is the power going to go up? Or is it going to be the complete opposite? Is the current going to go down and the power go down? So we kind of have to rely on our formulas here to figure this out. All right, so at 30 hertz, our new value of XC, which is 1 over 2 pi FC, is going to be 1 over 2 pi times 30 hertz times our 750 microfarads. And we're going to get a larger value of XC of 7.07 ohms. Okay, so we actually saw an increase in the ohmic value when we decreased frequency. So it could be said that when you start to increase frequency more and more and more, current is very easily stored and returned off of that plate, and the faster you do it, the less opposition to the change of voltage, and therefore the increased amount of current that can flow in that circuit is going to go up. And there'll be less and less ohmic value from that capacitor when the frequency goes up, because it's very easy for it to charge at first, and it starts to become more difficult to charge once the voltage starts to equalize with the source. So in DC, we see that our voltage of the cap rises to the value of the source, and we know that the current drops off basically to zero. And so what we're doing is, when we start to increase the frequency, we are in this period here where current is still very high. And if we decrease the frequency, what we see is we start to get more and more of this lower value of current with every single sine wave. So the longer we wait for that thing to charge, the lower the total amount of current that will be flowing at any given moment. It's kind of an interesting concept. So we decrease frequency, we expect less current, and therefore we get a higher ohmic value. So let's figure out what the new amount of current is. How about we try a marker that isn't dry? Here we go. So the new I total is going to be based on the new E total over the new Z total, and that is going to be 50 volts divided by our 7.07, and we get a new current of what actually ends up being 7.07 amps. Okay, so we got a much higher current, or sorry, lower current than we did here. Much higher current at 60 hertz, much lower current at 30 hertz. Last thing we want to do, let's just check out the quadrature power. So the Q of XL is I squared times XC. Sorry, the Q of XC. There we go, because we're talking about a capacitor. So the Q of XC is going to be our new current, 7.07 squared multiplied by our new value of XC, which is 7.07 ohms. Funny the way the numbers worked out there. And we get a new quadrature power of 354 points. Sorry, actually mixed my numbers up on you here. It's 353.4 VARs. There we go. And that's our new quadrature power. Okay, so when we had a higher frequency, we had a quadrature power of 700 VARs. The faster we flip that source back and forth, the higher the amount of current that can flow, because we don't have this charge on the capacitor that's going to oppose the source. And so therefore we have a lot more current, because we're higher in the current, and we have a much lower ohmic value of 3.54. When we lower that frequency, we see that we have a much higher ohmic value. Current isn't going to be as high because we're down here. We let that capacitor charge up for longer, and therefore the total amount of current and in average is reduced, and we have lower current and much lower VARs. All right. So very interesting circuit, and it's really starts to get to the point where you really want to just start trusting in the math a bit, analyzing the formulas, and sort of follow through, and then see if you can rationalize why that sort of thing would happen when you see a change in a circuit, for example, a frequency change. All right, so I hope you enjoyed this video, and we'll see you in the next one.